Hello, my name is Adolfo Neto. I'm a professor at the Federal University of Technology, Paraná, and this is the last class of our Introduction to Functional Programming class in 2021. And it's a series of very short talks. And we will start with Bruno Correia, who will talk about AWS Lambda for functional programming. You can share your screen, Bruno. You have 10 minutes.
Okay. It's opening here. Just a second, please.
We know that it takes a little bit for Meet to show the screen.
It's appearing something, no?
Yes, we can see you. It's just not only, yes, you have to start full screen. Okay. You can start.
Okay. I will talk about functions as a service with Elixir. I am Bruno Correia. I am an external student on University of Technology, Paraná. Well, what is function as a service? Well, it's a type of cloud computing service which puts a high level of abstraction between what we code and how it's running on the infrastructure beneath it. So we actually code something and we don't have to worry about the infrastructure, on machine, on the runtime, on any type of configuration on the machines under it. So the first company to release this kind of solutions was SpyCloud in 2010. I don't think this company is still existing, but well, AWS made it popular in 2014, and other cloud providers followed it, as Google Cloud Platform, Microsoft Azure, IBM, Oracle Cloud, and it's related to several use cases as batch processing, streaming processing, extract, transforming and loading, Internet of Things, and APIs. And well, it's popular because it scales, and cloud providers offer something called virtual infinite scales. So as long we can pay for it, and they can provide some more functional execution for us. Well, we just pay for what we consume, for the basically the compute time and how much times we execute a function. So we don't have to pay for machines or instances that are not in use. So in sometimes we have to scale our applications to provide the service, but when we don't use it, we don't have to pay for nothing. Well, if we develop microservices, the code is very simplified. It's very simple. So our functions holds little pieces of responsibilities, and they are cleaner to use and to write. Some, not all cloud providers have small data centers spread around the world, which can we use to deploy our functions to get closer to our customers and the function clients. It's basically depending on how we write these functions or its functionality. And on this type of architecture, it's faster to write and deploy and get it basically up and running. But there are some problems too. we have to write a function to this platform specifically for that platform. So it can be very hard to simply switch to another. Or we write a function for AWS, and to switch to Google Cloud Platform can be very hard. Testing our functions can be pretty hard when integrating with another functions. Having a testing environment can be challenging. Code starts where when we do not pay for instance to hold our applications, it will be only downloaded to some instance and then initiated when it's called, when it's invoked or triggered by somehow, and this can be increased. It's the execution time. We call it code start. Well, we do not manage the infrastructure underneath. We do not have how to ensure entirely the security for our own. So we rely on the cloud provider, on the vendor. And the cost can be a problem, but it can sound awkward because it can be cost efficient. But if we do not use it well, it can be an unwelcome surprise on an infinity recursion. Perhaps we can, well, can be a very serious problem when the abuse comes. Well, my implementation, I choose Amazon Web Services because I have a little bit experience with it. The view is based on how many times we invoke our functions and how much compute time they use it. The compute time is based on how much memory we have to allocate it with our functions. In the CPU time they will use it, it's proportional to the memory they will have. That number, it's equivalent to one vCPU, and one vCPU it's equivalent to one hyperthread. On AWS, you can use something called free tier, where we can use several services without any costs, and Lambda is one of them. We can invoke our functions up to 1 million times and 400,000 times gigabytes seconds of compute time. This is a kind of confusing number, but Lambda is billed by its computing time. So if we allocate 1 gigabyte to a Lambda and it take 2 seconds to execute, that's how we will pay for it. 2 gigabyte second in one request. It makes any sense until now? Any questions?
No, go on.
Okay. So AWS provides some runtimes: Node.js, Python, Ruby, Java, Golang, and .NET, and several versions among them. And Node has version 10, 12, 14. Python has 2.7, 3.5, no, 3.6, 7, 8, and 9. Ruby, I think it's 2 versions. Java, 2 versions. Golang, I think it's just 1 version, and .NET 2 versions. But no functional programming language runtimes is provided by AWS by default. So we have to provide it. AWS give us a way to do it. We can provide it in 2 ways: alongside with the function we are writing, or writing a Lambda layer. Lambda layer, it's a way to share dependencies between several different functions, different lambdas. that's how I choose to do my implementations. Another thing to to notice, it's Lambda functions must be invoked or triggered to be executed, and it can be triggered by other AWS services. I choose a Lambda layer to provide Elixir runtime to my functions and expose my functions as a part of the API through the API gateway services. So I created used this API gateway service, and this service will trigger my Lambda function. And my Lambda function must answer to this kind of a request, this kind of event. Okay, so this is how Lambda works. This is the Lambda platform. They have some APIs internally. My runtime should communicate with the runtime API. There are a few endpoints. Okay. There are a few endpoints that I use to communicate with it. And well, let's go. Now I will have to stop just a bit to show another window. Just a second. Okay. Well, the Lambda function must receive two arguments. The first is an event. That's the how well it's the arguments of the function. Maybe this can be little harsh to understand at first. And the second argument, it's the context, how the function is actually invoked or triggered. Then I use some, oh, it's a kind of the hello world. It's if it receive the name parameter from the API, it will respond greeting me or tell me that I must provide a name. This is my endpoint. Okay, it's actually working. If I do not provide a name, it's a hey stranger, you must provide a name. Okay, I am worrying a little bit about time. Sorry, I have to authenticate to show you something. Okay, here is the AWS Lambda interface to my actual function. And they provide some interface to test my functions with the events that I want to regarding the external effects. So I used some, I can just click here and, well, basically this. they provide an entire context and event. The event I use, it's basically I extract the body from, well, this entire big object.
Okay, and that's it.
Yeah.
And the idea is that you can build whole systems with these AWS lambdas, or just little features, microservice?
No, several we can do. Well, the best practice tell us to write microservices on lambdas. We can build several thousand applications with them, and the cloud provider worry about how to escalate them.
Mm-hmm. Okay. Yes.
It's more of our architectural feature than approaching to how to segregate application into small functions than actually coding itself. I thought maybe talk about how functional programming within function as a service is maybe it's a nice feature to talk about.
Okay. Any question, Luis, Leticia? I know Sam has just arrived, so he can't have any question, but or maybe he has, but okay. Then, Sam, can you present your work, your slides right now? Yes or no?
Yeah, I'd be happy to do that.
Okay.
Okay. I need to share my screen.
And thanks, Bruno.
You're welcome.
One moment. Sorry, just technical issues. Okay.
That's okay. I will publish this video for you as it is, but Sam, I asked then, so I ask you, is it okay if I publish this on my YouTube channel?
Yeah, that's fine with me. Okay, can you see my screen? You should see Jupyter notebooks open.
Yes.
Yeah. Okay, so the library that I was going to present about is it's called RxJS. It's a JavaScript and TypeScript library. It's actually written in TypeScript that makes certain functional patterns that work in a kind of asynchronous context available and easy to use in JavaScript. It's in many ways kind of similar to the Elixir Stream library. If you've worked with that, it's kind of very reminiscent. But okay, a little bit of history. The reactive extensions idea is actually it's a family of libraries. Originally started by a guy called Eric Mayer for .NET, but it was always intended as kind of a blueprint for other libraries in lots of different languages, so there could be a kind of common language. And there's versions in .NET, there's versions in Java, there's versions in JavaScript. There's a RX Python as well. I'm sure there's others that I don't know about. But the idea is to provide a blueprint for a library of observable streams in multiple languages. And yeah, the latest version, RxJS 7, has just been released very recently. So yeah, as I said, in terms of features, it's very similar to the enum or stream libraries, and the central insight of it is that events that happen over time can be treated as if they were lists. So just as we have various higher order functions that we can apply to lists or sequences, like mapping them, like filtering them, like reducing them, and many others. If we can treat things that happen over time, mouse clicks or messages coming down a WebSocket or things like that, if we can treat those as if they were a list, then we can also map over them to transform a mouse click into some information about the mouse click, its position or something, or to filter out certain mouse clicks and so on. And that can be a very powerful, functional patterns that should be familiar from functional programming, but make a lot of difference when you're doing asynchronous programming in say a JavaScript context. And these operations are higher order operations, as I've said, like map, filter, skip while, and so on. They're also immutable. So you take a stream which is a stream of messages from a WebSocket, and you filter them. And this filtered stream, this one's the first one still exists. It can still be responded to. You can still do things with it, and you have this new stream that is the filtered version. So these again, it's taking things from functional programming of this idea of immutability. So that's is that all fairly clear? I've got a little demo here, which I hope will work, which is kind of my live coding section. So what I've got here is I've
Sam, I'll just ask you to increase the font size a little bit.
Is that
It's
okay?
better. Yes.
Okay. So here's I've got a server that I'm not sure actually I can show you the code because I think it's only showing my current window. Maybe if you want to see the code for this server afterwards, I can mess with things and show you that. But it's basically a web. I wrote a little dummy WebSocket server that pretends to be Twitter. Twitter has something called I think Twitter's got something called the fire hose, which I don't think is generally accessible, but is like just a stream of all the tweets. So this is this is once I press this, I'll be running a server that's just sending to the client all these tweets, and then this here is a client that subscribes to them. So let's hope this works. Okay, nothing blew up. So now this is a bit of boilerplate, but the middle bit, I'm just subscribing to that stream of tweets and showing them. And okay, you're getting JSON, and I've got it randomly. I've got it in the back in my little server. It's got a list of tweets, and it's choosing them at random, and it's got a bit of a randomized interval between them. Okay, so then I have these various filter, map, and so on. So say I want to take this stream of tweets, and I only want to show the one I don't want to show the ones by Elon Musk and Jeff Bezos. I only want to show the ones by developers. So I've got the ones from José Valim and Guido van Rossum. I can take that stream of tweets and filter it to only have those users. And you'll see both of these streams are still existing. You're still getting all the ones up here from the original one, but down here you're only getting the ones that are by the developers. Okay, let's say I want to only get the billionaire tweets. I can do the same thing. And here, whenever I get something from Jeff Bezos or Elon Musk, it comes up there. But these are, again, you're seeing this immutability. Each of these new streams that I'm creating from the old one is its own thing. The old one still exists. We're still responding to it. That's filter. I can also, I can map them. So say I want to take the dev tweet, take the tweets, filter them for the developers, and then format them nicely into a nice little bit of HTML. I can do that, and by the next time we get developer tweets coming through, okay, you get them nicely formatted. You can, and there's more. I mean, this is a massive library with lots and lots of these kind of operators. Some of them are very easy to understand, like filter and map and so on. Some of them are quite complicated to understand. They take it, but for example, you can do things like, okay, I can filter here. I'm filtering out I'm filtering to only get the developers, and then I'm speaking to another API or something to go and take their usernames and get their real name, and then I'm formatting that, and then I'm and combining that with the current information, and then that's this concat map thing here, and then I'm mapping it again to a nice bit of HTML formatting. All of that's, if you're doing that in a non-functional way, that's quite a complicated, not to say unpleasant, and difficult to test, difficult to iron out all the bugs. With these sorts of functional patterns, it's really easy. It's really easy to test, because you can just feed in a sequence at one end. You can kind of turn this into a little function, feed in a sequence at one end, and see what comes out the other end, and just it's really good. And that's my talk. Does anyone have any questions or anything? I don't know how to stop sharing my screen, but
I have one question which is related. Is this pure JavaScript? You don't need anything else. You only have to import a library, or you have to have a special compiler for that?
You only have to import a library. It's written in TypeScript, but when they publish it to NPM, they build it. So yeah, I mean, I don't know if there might be a version on a CDN somewhere, so you can literally just put a script tag into your page. I'm not sure about that, but definitely if you're using, any of the kind of build steps that are common in JavaScript development now, yeah, it's just another library in that. Just npm install RxJS will get you it.
Okay. Bruno, Leticia, Luis, any questions? No? So thank you very much, friends. Oh, Sam. Friends.
That's okay.
I had to work with Node.js streams before, but if I had used this library, I think my life would be very easier.
Okay.
It's a nice talk. Thank you.
Thank you.
Thank you. And now we'll have Luis. He's talk about OCaml.
Okay, let me see if I can share the whole screen. Screen 1. Okay, is it working?
Yes.
Okay, so let's talk a little bit about OCaml. OCaml is a general-purpose programming language with an emphasis on expressiveness and safety. I took this quote from the official website because I think it describes quite well and quite concisely what OCaml is about, which is really about expressiveness and also elegance, but mostly safety. OCaml has a static typing and a great type system, and it also has great type inference. That means that while all the types in your program are checked at compile time, you don't have to type annotate your code. You can type annotate, but you don't have to because the compiler can figure out pretty well what you mean. It also has a great support for algebraic data types through tuples, records, and also variants. And it also has a very interesting kind of pattern matching with a lot of features that really emphasize the safety of the language. So a bit of history first. OCaml was created in 1996, and it comes from the ML family of languages, which is quite nice because it inherits the whole ML type system and type inference. So it's a nice background for OCaml. And it actually extends the camel dialect of ML. OCaml actually stands for objective camel, because in the beginning it was just an object orientation layer on top of camel. So OCaml is actually multi-paradigm. It supports mostly functional and it's mostly used functionally, but it also has object-oriented and imperative features. So let's get a bit into type inference. Just a disclaimer first, these code blocks, for examples, the first line is OCaml code, but the second line is actually the output that you'd get from a compiler or a REPL with the type signature and everything. So a basic example, you can just declare a variable and the type gets inferred. X is of type int. Here we're defining an anonymous function, and we say that it receives a parameter x and just return x times x. But here things start to get a bit more interesting, because in OCaml we have two sets of arithmetic operators. One set for operating with integers and another set for operating with floats. And the operators that operate with floats have a dot after it. So we can see that we are using an operator of multiplication on floats. So the compiler can already tell that x is in fact a float, and the return of this function is a float. And we didn't have to say it anywhere in the code. We can also have generic types. Here we are declaring an anonymous function that takes an argument f and an argument x. And inside the function, we basically apply f to x. This is the function application syntax. We just put the function and then the arguments that we're applying the function to. We don't have to write commas or parentheses, anything like that. And just for the use of f inside this function, OCaml can already tell that f is a function with this type signature. This type signature is actually alpha to beta, and x is of type alpha, and the return of the function is of type beta. And these are actually generic types. We don't have to specify an integer or a float or a string. This function will work regardless of the type of f or x. So this is actually a way of achieving parametric polymorphism, and there's more advanced uses of that. So getting into the basics of pattern matching, I would like to show an example of a simple definition of the map function that I think we are familiar with. But the basic concept is that the map gets a function and a list, and it will apply the function to every element in the list and then return the new list. So here we're defining a recursive function. In OCaml, you have to say explicitly that the function is recursive and can call itself with the keyword rec. So we're defining map, and map takes a function and a list, and we match the list with, and then we can say our possible cases of the pattern matching. If it's an empty list, we just return the empty list. But here we're matching the head and the tail of the list, and we apply the function f to the head and concatenate it with a recursive call of map with the same function to the tail of the list. And again, we can see the use of generics here. This function map would work with a list of elements of any type and with any function. And we don't have to actually specify the type, because the compiler can infer that the type is generic, because there's nothing here in the body of the function that depends of operations on specific types. Getting to a bit of algebraic data types, I'll talk mostly about variants, because I think they're quite different from what we've seen before. Variants are basically some types, but you also may know them for disjoint unions. And they're basically a declaration of a type. And with the declaration, you also have to tell all the possible values that this type can assume, that a variable or a value of this type can assume. And in OCaml, they're based on what are called constructors. So the most basic example that you can have of variants is a type color. And you say that a color could be either red, yellow, or blue. And in fact, you could declare a variable and assign it literally the value blue, and it will get inferred that the type of this variable is color. And constructors can be really values, but they can be more powerful than that. You can see, for example, if we would want to have a list with multiple types, because by default in OCaml, all the elements in a list must be of the same type. So if we try to do a declaration in this format, we are declaring a list, and the first element is 1, 2, and then we say hello, we would get a type error, because we started with an element of type int. So the compiler expects that all the subsequent elements would be of the same type. But in this case, we get a string. But we can work around that with variants. We could, for example, define a type called misc, and this type could be either an int or a string. And here we are still using constructors, but we are saying a bit more about the constructors. We are not only saying it's either int or string. We're saying that we have this constructor, and this constructor will carry a piece of data of this basic type. So it's an int of the type int, the base type int, any number, integer number, or a string of type string. And this enables us to do something like that. We can declare our list with elements, and we say the constructor, and then a value, constructor, and a value. And we can actually create a list, but actually all the elements in this list are of the same type, the type misc that we defined. So, but each element can also have a value that is of one of the basic types. So that's one kind of use of variants. Something very powerful about variants is that you can define parametric variants, which are a way of combining algebraic data types with generics. So here we're defining a simple binary tree, but we don't just define the type. We pass in kind of an argument, a type argument, which in this case is alpha. And here we're defining a generic binary tree. We're saying that a binary tree can either be a leaf, and this leaf will carry an element of type alpha, or a node, and a node can have a binary tree. And this star here is actually we're defining a tuple. So it will be a binary tree on the left, and a value of type alpha, and then a binary tree on the type on the right. So we could have a definition like that using this type. And here we're creating a binary tree with elements of type string. And with the same definition, if we declare the binary tree with elements of type int, we could have a binary tree with integers with the same generic declaration. So this is quite powerful when you start to think about user custom data types with generic declarations. Okay, so a bad name for the presentation. But before I go on to the live coding, anyone has any questions until now?
No.
Okay, so let me just put this aside. Okay, I would like to show a bit about how we can combine variants and custom-defined data types with pattern matching. And I think it's quite interesting in OCaml. So let's say that we want to write a little program that can have shapes, geometrical shapes, and then we want to operate on those shapes. So we can have a simple, the most basic definition, which is a point in the Cartesian plane, which is just the x and y coordinates. And then we can define our shapes. And let's say that a shape can either be a circle, and a circle would have a center, which is a point, and it has a radius, which is just a float. And we could also have a rectangle, and with a rectangle, we could have just the lower left and the upper right points. I think that's enough for this demonstration here. And with this type defined, we could, for example, write a function that will return the center of a shape, for example. So we can write a function that will operate on our custom type. And the cool thing is that we can actually pattern match on the constructor of variants. So our function gets a shape, but it's different. In our case here, the calculation for getting the center of a circle is different from the calculation to get a circle of a rectangle. So in the case it's just a circle, we can just match the center of the circle and just return the center of the circle. And here we're already getting an error. And it says that this pattern matching is not exhaustive. That's because OCaml can already tell that because shape can be a circle, shape is actually of this type shape that we defined. But it also knows that an element of type shape can also be a rectangle. So our pattern matching can fail here. So if we add the rectangle pattern match here, it won't complain anymore. So a simple way of getting the center of a rectangle with this definition is just to have the average between the 2 points, the x and y coordinates. So we can get it like this. And you notice that I have to specifically define the operators for floats here. I can't do this because it's a type error. So you see, depending of the value of the variant that we're getting here, we will do different things. So we can quickly test this in a REPL. Let me use this directive here. Okay, so we can define our little circle with a center, which should be any value here. And we can also have a rectangle. Which will have a simple point here. And if we apply center to the circle, if I can type correctly, just returns the center point. And if we apply to the rectangle, it takes the average of the 2 points. So it's a very simple example, but it kind of illustrates how you can combine pattern matching with variants. And I thought it was very, very cool when I discovered that you can do that. That was it for the live coding. Let me stop sharing.
Okay, thank you very much. I believe Sam has a question.
Yeah, I guess because of the common ML heritage, reminding me a little bit of what I've been reading about Haskell and stuff. Does it have anything like type classes or Elixir protocols? Because I was thinking, what I was with your circle example, with your center example, where you were pattern matching on the types. I was thinking of like in Haskell, where you'd have various different types that have instances of a type class, center, and then you can have that sort of polymorphism, and you can, protocols as, I hesitate to compare it with Haskell and Elixir. They're quite, but protocols do a similar thing, kind of. Does it have anything like that?
Yeah, I'm not quite familiar with the concept of type classes in Haskell, but in Elixir, protocols are a way of achieving polymorphism, right? So I think it's kind of like that.
Yeah, so the idea of type classes in Haskell, for example, is you might have various different unrelated types, but they all implement the equal type, the eq type class, which means that for each one you define a function that will let you compare them to others of their type, and then you can have other functions that just let you do something with anything that has the equal type class, or something like that.
Oh, okay. That's
it's that sort of polymorphism. It's difficult to explain in the abstract. I'm sorry.
yeah, but I think I got the idea. But I don't know how to answer your question because I don't know if OCaml has that. I never heard of it, but I'm also studying it just like it's been just a week. I think you can achieve some kind of polymorphism, but it's like in a module level because you can use parametric modules in OCaml. It has kind of this whole hierarchical thing, and you can pass parameters to modules so they can work with types. It's a bit of crazy integration, but I don't think it's quite at that level that you're saying. But I'm not sure.
Thank you.
Thank you very much, Luis. I can see the beauty of OCaml. I can see why so many people really love this language, because there's this guy I follow on Twitter. His name is Camilo. He really loves. He's producing a lot of content about OCaml in Portuguese, and it's very interesting. And last week there was ICFP, the International Conference on Functional Programming, and they had I believe it was a whole workshop about OCaml, lots of talks, even one by the creator of OCaml. It's going to be on YouTube, I believe, soon. And also there was a talk. It was not a talk, it was mostly a conversation with a guy from a big company, I believe, Bloomberg. And he said they use OCaml at Bloomberg. And that's very, very interesting. Thank you very much. And now for the last talk today, it's Leticia, who will talk about the functional features of Rust.
Yes. Oh. I'm going to share my screen.
Okay.
Can you see the presentation or not?
Yes.
Okay. So my name is Leticia, and I'm going to talk about Rust. Here I just made an example in Elixir because Rust is actually a multi-paradigm language. It means that you can actually program in imperative, object-oriented, functional, and many others. So we are discussing the history, some characteristics, functional features as examples, and live coding. Rust was created by Graydon Hoare when he worked at Mozilla. It actually was his personal project, but he showed his project to his manager, and they thought that it was great to start sponsoring because it had a lot of potential, and it will be great to recreate Mozilla in a faster, safer, and more concurrent technology than C++. So after some experimentation, the first version was released in 2015, as well with Cargo, that is a pet package manager for Rust, and Crate, that it's package repository. So, okay, before that, who quitted Mozilla in reason of emotional burnout, but since Mozilla was sponsoring the project, it kept going. Currently, the last version is 1.54.0, and anyone can contribute to the language by writing bug fixes and improving the documentation by pull request on GitHub. From 2016 to 2051, Rust won the Stack Overflow server from most loved language. It's 6 years, so it's a lot of time. People really love Rust. Some characteristics from Rust is, as I said, it's a multi-paradigm language. It's compiled, and it provides a foreign function interface to C, so you can export functions from C to Rust and from Rust to C really easily. It does not use a garbage collector because it has fearless concurrence. It's just a method that the compiler analyzes in compile time if some data is really useful in that scope, and if it's not, it already eliminates, and it makes the use of memory way more efficient than C, and it's really safe because you eliminate the possible breaches in the system. Oh, okay. It was influenced most from software language and functional language. So data types was based on C, Limbus, Malloc, Lisp. Function programming was from Haskell, Camel, and F#. And the rest is basically or really low-level language that have low latency and are used to this purpose, or some functional. So Rust has some inbuilt functional features as immutability, function as first-class citizens, and pattern matching and closures. So it's a really simple example, but immutability is the default way to declare variables. Unless you set the mult keyword, you're going to have immutable variables. It means that if you try to change a value that was set to a variable, you get a compile error. So if you declare let age as 35 and you try to change the value to 6 or any other value, you get a error. But if you want to change the value of the variable later, you can set as a mutable variable. In Rust, functions are first-class citizens, so you can pass another function as a parameter. In this example, you have two variables that are floats of 32 bits. And you have answer that receive the result from the function calculate, which receives the sum function and the two floats. So in this example, you just have one function that is sum, but if you want to program a calculator, you can actually create a division, subtraction, and multiplication function. So it will receive the two floats and call the operation in the line 6. In Rust, we also have pattern matching. Actually, the equal symbol is matching. So when we are assigning a value to a variable, you're actually matching the right side to the left. In this example, you are matching x to 1, epsilon to 2, and z to 3. And we also have the match function. So if you pass a string, you can match to another values. In this case, Elixir has functional style, and Rust can work functionally as much as you want. And we also have the underscore that is always going to match. And closures, they're basically a way to declare anonymous functions. So we can assign a definition to variable. In this case, closure is the anonymous function, and we receive num, that is an integer of 32 bits, and we return another integer of 32 bits. So it basically adds 1 to the num, and you can call as closure and the value. Okay, now I'm going to share another screen. Before that, anyone has any questions?
No.
Okay. Okay, can you see my screen?
Yes.
Okay, so I just thought about making a function about vaccines. So we can have a name of someone as Paulo. His ID, the ID stands for the ID of the vaccine, so we can match the name and the code. I'm going to hard code to be faster, so that's it. So here we're receiving a num, and which is an integer, and we are going to match the num. And if it's 1, we're going to call a function. By the way, I'm going to create them before. I'm going to name them as the name of the vaccines.
Could you increase the size of your font a little bit?
I'm not sure how to do that in VS Code. Is there a way to?
It's
Press zoom.
Shift Control and plus.
Oh, okay. Is it okay?
Yes, much better. Much
Okay.
better.
Okay. So we also have Pfizer and Janssen. Okay. So if it's 1, we're going to call AstraZeneca to Pfizer and 3 Janssen. And if no one's matched, you're just showing an error. Now I'm going to create another function that I'll call shots, and will receive the closure or the function. Okay. Oh, actually, it's not going to return anything. Yes. The name of the person and the ID. Now it's going to change to show a message like welcome and the name, and then we'll call the closure with the ID. And right here, I will show a message. Your shot is from AstraZeneca. The second one will be in 3 weeks. And then
I believe AstraZeneca is 3 months, right?
3 months.
Yes, I know because I took one.
Okay. I did a quick search before. I can be wrong because
yes, but maybe it's only in Brazil that it's 3 months.
Right.
Maybe all over the world is 3 weeks.
Okay.
We have the logistic problem, no? So
Yes, yes, we have. I can be wrong. Sorry, I can check later, just to not, send incorrect message. Pfizer is 4 weeks, and Janssen, you don't need another shot. So I show. Oh, okay. What I did. Oh, I just forgot semicolon here. Okay, I did some mistakes. Oh, I did not use name. Oh, it's okay. That makes sense. I have to call the functional here. The function here. Oh, it's closure and the name and the ID. Oh, it's okay. So the ID is 3, which means you're going to take the Janssen shot, and you can have the 1 or 4. Okay, just had an error, and that's it.
Okay, could you show the code again? Yes.
Yes.
So you're just using shots.
Yes, I'm calling
Yes.
shots and passing the closure to it.
Okay. Shots is the function that does the interface. So Bruno wants to ask a question.
Can we do pattern match on the function definition, or we have to use the match?
We have to use it with the match. There are some libraries. I don't think that they implement the pattern matching, but they do have some hash table. But for now, it's just the match for each.
Okay.
Okay. Anything else? No. So, where's the cat?
Oh, I think
You cut the cat. That's okay. I was.
That's the cat.
Oh, I wasn't paying attention. I was just reading the Let's Code. Okay, thank you very much.
Thank you.
And yes, that's the end for. Let me stop the recording.